You know that device you're probably holding in your hand or watching this on right now? It's not just a smart piece of tech, it's an absolute miracle of physics. It's a little portal to the world, built on principles so bizarre they make you question reality itself. In this explainer, we're gonna go find that hidden science. All right, so let's just dive right in. We hear this term all the time, right? Quantum mechanics, this weird, spooky, subatomic world. But where is it actually hiding inside the phone that's in your pocket? It feels so disconnected from our day-to-day lives, but as you're about to see, it is literally the bedrock of your entire digital world. So, to find this physics, we've got to peel back the layers. We have to look right past the shiny glass and the cool metal case. The real magic isn't on the surface. It's buried deep inside the electronic heart of the device. At the very core of your phone, there's one single, incredibly powerful component, the system on a chip, or SoC for short. You can think of it as the device's brain, its command center, everything, all squished into one tiny package. Our search starts right there. Okay, now we're going to zoom way in on that chip. We're going from something you can hold in your hand to a scale that's, well, it's almost impossible to really wrap your head around. To find out where all that power comes from, take a look at this number. 10 billion with a B. What in the world could your phone possibly have 10 billion of inside that tiny little chip? It's not pixels, it's not songs, it's not even lines of code. It's billions of one single physical thing. That's right, switches. More than 10 billion microscopic, electrically controlled switches, all crammed onto a sliver of silicon about the size of your fingernail. Every single thing your phone does, sending a text, scrolling through photos, watching this very video, it's all just these tiny switches flipping on and off at insane speeds. And these microscopic switches, they have a name: transistors. Now, the easiest way to think about one is just like a light switch. When it's on, electricity flows, and that's a 1. When it's off, the flow stops, and that's a 0. Everything your phone does is just built from billions of these ones and zeros, flipping billions of times a second. Now, to be specific, the real hero of our story is the MOSFET. That's the particular type of transistor that has made all of this incredible miniaturization possible. It's the fundamental building block, the absolute workhorse of our entire digital age. So the big question is, what are these amazing little switches actually made of? To build billions of anything this small, you can't just use regular old metal or plastic. No way. You need something special. You need a kind of miracle material, one with a very particular set of skills. You know, most materials fall into one of two camps. You've got conductors, like copper, that let electricity flow easily, and then you've got insulators, like rubber, which stop it cold. But there's this weird middle ground, a class of materials that can kind of play for both teams. We call them semiconductors. And that right there is their superpower. A semiconductor, like silicon, can be precisely controlled. It can be told when to act like a conductor and let the juice flow, and when to act like an insulator and shut it all down. I mean, engineers can change its conductivity by a factor of 1,000,000 or more just by tweaking its recipe. That level of control is the whole game. The secret sauce for this is a process called doping. You start with incredibly pure silicon, and then you intentionally add tiny, controlled amounts of other elements. These are the dopants. And doing this creates two different flavors of silicon: N-type, which has a surplus of electrons just waiting to move, and P-type, which has a deficit, or holes where electrons would love to settle in. Now, on their own, N-type and P-type silicon are, well, they're kind of interesting. But when you join them together, oh man, that is when the magic happens. You create the absolute core of all modern electronics. And this is where things get really weird and where we finally find that quantum physics we were looking for. The spot where these two types of silicon meet is called a PN junction, and it is everything. It's the heart of diodes, LEDs, solar cells, and of course, our good friend, the transistor. It's a really simple structure, but what it does is profoundly important. So what does it do? At its core, a PN junction is a one-way gate for electricity. It's like a bouncer for electrons. It lets current flow in one direction, but totally blocks it from going the other way. This simple behavior is a cornerstone of electronics. But as these components get smaller and smaller, their behavior gets a whole lot stranger. See, as we've shrunk these components down to just a few nanometers in size, we're talking just a handful of atoms across, the old classical rules of electricity just don't quite cut it anymore. We've actually had to start using the weirdness of the quantum world itself to our advantage.
And here it is. It's a phenomenon called the tunnel effect, and it is purely quantum. In our everyday world, if you don't have enough energy to get over a wall, you're stuck. But in the quantum world, an electron doesn't need to go over an energy barrier. It has a probability of just, poof, appearing on the other side, like it tunneled straight through the wall.
And this isn't just some quirky idea from a textbook. As transistors have shrunk, their internal insulating layers are now only a few atoms thick. At that scale, electrons actually tunnel through them all the time. And here's the wild part. Engineers don't fight this quantum weirdness anymore. They depend on it. This effect is now an essential part of how your phone works. Okay, so let's zoom all the way back out and see how that one strange quantum rule connects all the dots right up to the phone that's in your hand. So here's the whole chain of logic, from the quantum world to the real world. The bizarre rules of quantum mechanics allow for the tunnel effect. That effect is now critical for how tiny PN junctions work. Those junctions are the building blocks for transistors. Billions of those transistors make up the chip, and that chip is the brain of your phone. It's all connected. So the next time you pick up your phone, just take a second to remember what's really inside. Its foundation isn't just clever software or sleek industrial design. It's dense, complex physics, the kind of stuff you'd see in the university courses we've based this on. The abstract has become very, very real. And it just leaves you with this one last thought. A century ago, the quantum physics that powers your phone today was just a collection of abstract theories on a blackboard. So what future magic, what next game-changing technology is hiding inside the physics equations being written on blackboards right now?